In this lecture, we are going to give a brief introduction to the aspects of differential geometry that we are going to need in this course. It will be very basic topics, and if you want something more precise, rigorous, and advanced, you will have to attend the course on advanced gravity. There are two main reasons why we need to study differential geometry. The first of them is that, as we saw in the previous lectures, the Einsteinian equivalence principle in the end led us to formulate this principle of general covariance. The principle of general covariance told us that we basically had to write all physics in a covariant way, covariant under general coordinate transformations, or what is briefly general covariant. This means that we have to study coordinate transformations and that we have to define objects that behave well under coordinate transformations, and this will be the main tools or the main objects that we will use in constructing our theories. There is another reason why we need to start studying coordinate transformations and differential geometry. If we didn't have to perform coordinate transformations at all, we would just decide which coordinates to use, and maybe once in a while we would say, okay, because this problem has spherical symmetry, let's work in spherical coordinates. But otherwise we would be using basically one coordinate system for all the universe, and that would be it. There is a reason why this is just not possible, and we are forced to study coordinate transformations from the very principle. The reason is that most geometrical spaces cannot be described in a single coordinate system. So you have to imagine that your geometrical space, let's say that it is this screen where I am drawing, has some regions, not as regular as this one. Let's say that just more like a potato, on which you can define some coordinates which are similar to the coordinates of R4. So if we are in 4 dimensions, it will be maybe curved or whatever, but basically these are R4 type coordinates. However, your space, or like this screen, is really bigger. And these coordinates may not be able to cover all of it. One example would be these spherical coordinates we were talking about. They are really bad at several points. For instance, at the origin r equals 0, they are not good coordinates. Good coordinates are coordinates such that you need the 4 numbers to distinguish uniquely one point. In spherical coordinates, r equals 0, for all theta and phi indicate the same point, the origin. So there are many sets of coordinates that refer to the same point, to the origin. These are really not good coordinates. There are other points where these coordinates fail. But you can imagine a situation in which, the region where it fails is this boundary that I have drawn here. Then what do you do to describe the rest of the space? And this may be this looks like a problem that is tied to a bad choice of coordinates. But this is the general situation. You're going to choose, in general, better coordinates. You can choose coordinates which are good in some region. Then what happens if you want to give coordinates for a point here and the neighborhood of that point? Well, you have to choose another coordinate system that will be good in some other region. This will be some other coordinates which will be similar to R4 coordinates, some R4 set of coordinates. But what happens for points in between? Okay, at some point you will find that you have to use coordinates in sets that overlap. And then you will find that there will be points which can be described in two different sets of coordinates because they belong to of these different regions that we are going to call in a very non-rigorous way, but also very common in the literature, coordinate patches. Then you will find points that can be described in two different coordinate systems because they belong to two different coordinate patches, and you have to find how to express the results that you obtain in one coordinate patch using one coordinate patch to the language of the other coordinate system. Okay. So you are forced to consider these situations, otherwise you would find something inconsistent. You would describe the physics in the neighborhood of this point using this coordinate patch. Let's call this u1, u2, and u3, and the coordinates x1 mu, x2 mu, and x3 mu, or better, x mu, y mu, and z mu. Okay, if I do physics using these coordinates y mu, then it should be equivalent. I should get exactly the same results as if I do physics using these coordinates. And by the same results, I mean results that can be consistently transformed into results written from one language to the other. This is what consistency means here. And the same results. Okay, the same results. Does not mean exactly the same numbers. Means results that can be transformed consistently between one coordinate system and the other. So the consequence of this discussion is that we have to study coordinate transformations, and we have to find objects that transform well under these coordinate transformations because they are unavoidable. Okay. First, there is a physical requirement that physics should be independent of the coordinate system we are using, at least the form of the laws, although the values of a specific magnitudes can be different. And secondly, these coordinate changes are unavoidable if we want to describe physics in the entire spacetime, because this entire spacetime may not be covered by a single coordinate patch. So, if we are in this situation that the coordinate patches u1 and u2 overlap, what do we mean by saying that in the intersection of u1 and u2 we can change from the coordinates of the patch u1, which are these x mu's, to the coordinates of the other patch, which are y mu's? Well, it certainly means that we have probably some expressions of the coordinates y mu in terms of the x's, and that this expression is one-to-one and therefore invertible, at least in that intersection. Okay, so this will exist, and this change should also be differentiable. So these conditions together mean that if we define the Jacobian matrix of this coordinate change in this way, then this matrix should be non-singular, therefore invertible. Remember that the inverse will be given by these partial derivatives. And okay, if we can do this systematically and cover the whole spacetime by these coordinate patches, such that in the overlaps the changes of coordinates are one-to-one, differentiable, Then this kind of geometrical space, which is the geometrical space in which we will do physics, is called a differentiable manifold. Okay, there are more technical conditions that one has to ask for a geometrical space to be a differentiable manifold, but we will just be happy assuming that these patches are nice enough to do physics in them. So let me finish this discussion of coordinate changes that has led us to the concept of differentiable manifold with a simple description of or an intuitive description of what a differentiable manifold is. You can say that a differentiable manifold is a space that locally, and locally means in a neighborhood of any point, where we can have a coordinate patch covering that neighborhood, is a space which locally is similar to R4 if we are in 4 dimensions, or Rn if it is an n-dimensional manifold, but globally it may not be. Okay, the fact that locally it is and globally it is not means that you have to add some consistency conditions to patch up these neighborhoods on which it is similar to Rn, and all these coordinate changes, the fact that you have these transformations of coordinates which are invertible, one-to-one, and differentiable. Okay, these are, by the way, diffeomorphisms. Follows from this from trying to make rigorous this definition of differentiable manifold. Then, which kind of objects can we define in these geometrical spaces? There must be objects such that if I define them in one of these coordinate patches, and in particular in a region in which there is an overlap with another coordinate patch, I can consistently relate the values of these objects in U1 and U2. So they must transform nicely or in a well-defined way under these diffeomorphisms, under this the kind of coordinate transformations that we are considering here. These objects are tensors and also a slight generalization that we will see at the very end, which are called tensor densities.